In this video, we will look at some graphing basics and types of variables. Our objectives are to identify independent versus dependent variables. We'll look at two main types of graphs, linear and curves. We'll understand the meaning of what an intercept for a graph is. We'll look at identifying increasing and decreasing graphs. And we'll look at the quadrants of a two-dimensional plane. We'll start with the definition for variables. Variables are categories that represent quantities. To illustrate this definition, let's look at an example where we go out to eat at a restaurant. Some possible variables may include distance to the restaurant, time involved, number of people joining, and the cost of the meal. In mathematics, we also label each category with a symbol to represent each category. We don't want to get too complex or creative in our choices for symbols for each category, and the typical scheme we'll use is we'll just take the first letter of the main descriptor of each variable. In this case, I chose the letter D for distance, T for time, N for number of people joining, and C for the cost of the meal. Moving along, we'll now look at independent versus dependent variables. We'll use the letters X and Y as our variables. Think of Y and its values depending on whatever X and its values are going to be. When that is the case, we say that Y is a dependent variable and X is the independent. In other words, Y depends on X. To help us make more sense of this definition, let's return to our scenario of going out to a restaurant and all the variables we created for that scenario. Let's consider two variables on this list. And what we're going to do is decide which one is the dependent and which one's the independent. So let's take the very first two, D and T, distance to the restaurant versus time involved. And we're going to reason, how does one depend on the other? So I claim that the distance to the restaurant is going to affect how much time is involved in going out to the restaurant. In other words, time depends on distance. So just to make it simple, if the restaurant was a block away from the starting point, and the time involved in getting to the restaurant will be much shorter than if the distance to the restaurant was much greater and it required more time to travel there. So we conclude that time, T, depends on distance, D. And finally, let's take, just for one more example, two variables at the end of the list, number of people joining N and cost of the meal C, and decide which one is the dependent and independent. So I would argue that the cost of a meal is going to depend on the number of people joining. So if there's only one person going to this restaurant, the cost of the meal, let's say, is $10. But if 4 people join, then the cost of the meal could perhaps go up to $40. So C depends on N. We call this the two-dimensional plane. We have in front of us a vertical line and a horizontal line. We call axes. We have what is called a vertical axis and a horizontal axis. And these axes are really number lines. So you have a number line that starts at 0 and goes upward in the positive direction. And every mark that you see is the location of that value. And the same goes for the horizontal axis. The horizontal axis is really a number line. And in this example, I'm showing you that it starts at 0 and moves onward to the right hand direction, which is what we call the positive direction. Returning to variables, we'll see how variables and axes relate. The values of the dependent variable will belong to the vertical axis, and the values of the independent variable will belong to the horizontal axis. To make this idea more concrete, let's reintroduce the variables from the previous example about going to a restaurant. We'll use the variables C and N, the cost of going to the restaurant and the number of people going. Recall that we established that C depends on N. So C will be on the vertical axis as a dependent variable, and N will be on the horizontal axis as an independent variable. Now we'll look at what a possible graph between these two variables might look like. To start the graph, we could start it at the origin, because if 0 people go out to the restaurant, then the cost of the meal will be 0 as well. Earlier I mentioned that perhaps if one person went out to eat in this scenario, then the meal would have costed $10. And if 4 people would have gone, then perhaps it would have costed $40. The graph in that sense would look like a line that starts at the origin and extends upward in a diagonal direction. This style of graph an increasing linear graph. Increasing because if, let's say it starts at 1 and there's a certain dollar amount associated with that, then when you go to a n value that's bigger than 1, you'll obtain a larger vertical value. So that's the increasing sense. The linear just means that every 1 unit across the n-axis, you're going to see a c value increase by a proportionate amount. Let's now look at a different pair of variables. We'll look at time and the number of workers involved. Now let's just suppose these variables pertain to a job being done. And it's such a job where it takes more time with the lesser amount of workers. As the number of workers increases, then we'll see the amount of time required to do the job go down. So a possible graph that we can have in this kind of situation would be a decreasing linear graph. And the reason why we think of it as decreasing is because if we thought of time as minutes on the vertical axis starting at 70 on the left side of the graph, as you move your way to the right along the graph, the values of t start to decrease as the values of n increase towards the right. Another possible graph would be a decreasing curve. We now look at 2 special points that are part of a graph in their relation to the axes. When a line or any graph crosses the axes, we give names to these special locations. The first one on the vertical axis we call the vertical intercept, and the one on the horizontal axis we'll call the horizontal intercept. Now let's suppose our dependent variable is y and our independent variable is x. Then at the vertical intercept, the independent variable has a value of 0, and this will always be the case at the vertical intercept. The value of the dependent variable at the horizontal intercept will be 0, and this will always happen. We'll now look at the last topic of this video, and it pertains to the two-dimensional plane as a whole. So far we've been looking at the positive axes of the two-dimensional plane, and we call this a quadrant, and that is the 4 quadrants that are created with 2 extended axes. So we call the one at the top right quadrant 1, and Roman numeral I is used to represent number 1. And then going to the left from there, we have quadrant 2, followed by quadrant 3, and quadrant 4 underneath quadrant 1. Now, Roman numerals are just optional. You can also use Arabic numerals. So most of this video we were focused on quadrant 1, where we were using the positive value axes. But when we go to quadrant 2, we see that negative values are what are found on the horizontal axis. Meanwhile, you'll still be using the positive vertical axis when you're in quadrant 2. As for quadrants 3 and 4, we now notice that we are using the positive horizontal axis and the negative horizontal axis, but the vertical axis will be negative. We'll now summarize what we've seen about quadrants by considering a curve that crosses all 4 quadrants. And in particular, we'll look at the points on the graph corresponding to each quadrant. Now, the thing to walk away with here is that each point is represented by an ordered pair. In other words, a pair of values that are either negative or positive, maybe both positive, maybe both negative, or a combination of negative and positive. Remember that the first component on the left side of the ordered pair corresponds to the horizontal value that it lines up with, and the second component on the ordered pair corresponds to the vertical value or that it lines up with.